I'll begin with a word prayer. Heavenly Father, we thank you for this day, and again for my wife's delicious cookies. And I just pray you be with us. Help us to review well for the test tomorrow, Lord. In your name I pray. Amen. Okay, so first things first, yes, we are missing the solution to the problem 10 on the math battle. Let's work that out right quick. What was the problem? To integrate, what were we supposed to integrate? Sigma r squared dm, was it? Or ds? And that was over the sphere, right? Radius equal to r. So the sphere centered at the origin. And so this was a constant. So we can bring that out front. And then I'll keep r squared like it is. What's ds? Well, ds, I'm sorry. Let's see here how to say this. So we have r squared, ds is actually, stink. So we worked this out before. The surface area element for the sphere is r squared sine phi d phi d theta, right? For the sphere. And so we're supposed to put, and so, well, here this r is equal to rho sine phi. So that says that r is actually equal to r. Yes, we know there's an Amber Alert. We got it. We got it. We're inside. We can't help you. No one's stealing. Yeah. No one's abducting the child to Demoss. Relax. All right. Sorry for the child. Let's see here. So, and/or old person. I never know. But, it's an Amber Alert. That means young person, right? Is that one of those, what, the silver alert, or we call it? I don't know. So many alerts, I lose track. Let's see here. Okay, so my point was that this r should be evaluated on the sphere, right? On the sphere that we're working, we have r is the radius. It's, r squared is what? It's the x squared plus y squared, that r, right? So that is also equal to rho sine phi. So when we put rho equal to r, we get r sine phi. So this r squared gives us r squared sine squared phi. That's from the r squared, from this r squared. And then the ds is big R squared sine phi d theta, right? And I guess we're going from 0 to pi, 0 to 2 pi. So we got sigma r to the fourth, right? Times 2 pi, that's the theta integral. And then integral from 0 to pi looks like sine cubed phi d phi, right? So we can go through this integral again, but maybe you remember that's 4/3. And so what we get is 8 pi sigma r to the fourth over 3. Do I need to review how to go through the integral sine cubed again? All right. I can do that. That sounds relaxing. I'm teaching how to do this online in the fall. It's right here, this one. We're going to do this online. It's happening. How am I going to keep students from cheating? Is an interesting question. I don't know. Is it a time test? Yes. But I also have to allow time for like scanning and such. So it'd probably be like the time for the test plus 40 minutes for like scanning the test, and we're still having paper tests. So, I mean, so it's at least still somewhat real. Let's see here. Okay, so what do we got here? Then you let u equal to cosine phi, so your du is minus sine phi d phi. And so we've got, and by the way, u of 0 is 1, u of pi is minus 1. So we get integral from 1 to minus 1, 1 minus u squared minus du. I would flip the bounds, integral from minus 1 to 1 of 1 minus u squared du. So we get u minus 1/3 u cubed evaluated from minus 1 to 1, which gives me 1 minus 1/3 minus minus 1 minus 1/3 times minus 1, also known as 2/3 plus 2/3, which is 4/3. Yeah. Sorry, this is a rerun. We did this one already this semester. Now, what if I wanted to, so this was the moment of inertia of a sphere of constant surface density sigma, right? So that describes the, if you were to rotate with angular velocity omega, the kinetic energy would be 1/2 I omega squared. This is the I. Now, if you wanted to state that in terms of the mass of the sphere, how would you do that? If I want to eliminate sigma and write it in terms of mass instead, what's the mass? What's the mass of the sphere? Integral of sigma ds, right? Over the sphere, yeah. So sigma is a constant. So what's the integral of ds over a sphere? We worked this out already, right? This is something you probably should know, especially for your physics course. What's the surface area of a sphere? Yeah, 4 pi r squared, yeah. So we can solve sigma actually is equal to the total mass divided by the total surface area, which is 4 pi r squared. So you could put that back up and figure out that the moment of inertia is, what is it? Looks like 8 pi over 3 times m divided by 4 pi r squared times r to the 4th, which works out to what? What's the moment of inertia? Pi's cancel. What's 8 over 12? 2/3, right? Hey, didn't we work this out before? I feel like I did this. Did I do this? I feel like I've talked about 2/3 versus 2/5 in a previous lecture. 2/5 was the moment of inertia for a solid sphere versus 2/3 being the moment of inertia for a spherical shell, which is what we just worked out here. Hey, we have done this before. So don't ask me which day. I just know it was this semester. Pretty sure. Okay, so what should you be ready for on the test tomorrow? What would you expect? What would you expect a question on the test would look like? Like, you're going to have lots of questions saying, here's a vector field, calculate the divergence, calculate the curl.
That'd be awesome.
Yeah. It is likely that that will be part of the test, but it might be part of a larger question, right? Like use Green's theorem, or use the divergence theorem, or use Stokes' theorem to calculate such and so forth, right? Okay, so divergence theorem. In case you haven't noticed already, what's the divergence theorem say? Also known as Gauss's theorem. It says for a simple solid, we have that the triple integral over E of the divergence of a vector field F is equal to the flux through the boundary of E of that same vector field. So, of course, there's a more nuanced form which allows for the simple solid to have a hole inside, right? Then we have to take the inner surface to be inward oriented. Remember that? So there's a fancification, if you will. This gets it looks the same, right? But there is a fancier version of this. Well, well, let's not say E. Let's say, I don't know. I need another letter. Give me another letter. Do a letter for me. What's that? B? All right. So boundary B. So here's a picture, roughly. So this is a cutaway, right? And so maybe this is B. So the boundary of B is understood in that theorem to be the positively oriented boundary of B. And it's pretty simple. That means that the normal to the boundary of B points out of B. So on the outside edge, it means that the normal looks like this. Like this. But on the inside edge, the normal points like so, right? So here so that there's, this. But the larger point here is if you're going to use the divergence theorem, what kind of surface do you need, really? Unless there's some kind of extra kind of sneaky thinking involved. You need a closed surface, right? Surface that goes all the way around and wraps around something. On the other hand, Stokes' theorem is not like that, in the sense that Stokes' theorem says that the integral over surface of the curl, the flux of the curl through the surface, is equal to the line integral, the circulation of the vector field around the boundary of the surface. And here, this surface does not have to be a closed surface, right? It could be just some kind of thing like that, And it could, it could also have holes, right? It could have holes. And so the surface could be like this, right? I can't shade, sorry. And then, so the boundary of S, as we've described, imagine yourself a little dude walking along the edge. He needs the surface to be on his left. Yep.
So you said the surface S is not closed?
No.
Why not?
Why not?
Or
Because it has a boundary. So a closed surface is one which the boundary is nothing. What's the, if you take a basketball, what's the boundary of a basketball? No, that is the basketball. I mean, so think about, yeah, you got me. Just the skin of the basketball. What's the edge of the skin to the basketball? Like what's the boundary to that? I mean, so the way a boundary point works is if you take such a point, well, good grief, I don't know how to describe it technically in here. I know it when I see it. So the boundary here, really, the boundary, we make it simpler. This is the disk on the board. All right? And here is a hole. So I want S to be this thing right here. All right? The boundary for S is the edge of it. So like this is a boundary point, or that's a boundary point. But let's see, the positive orientation. Now there's a question, is this S have a normal that points out of the board or into the board? Because that determines which way is up. So supposing that this normal to the surface points out of the board, all right? So you imagine yourself walking on the board, actually, along the edge. You can see that you have to walk counterclockwise, right, to be positively oriented up there, whereas you have to walk clockwise, rather, in the interior hole. That's the positive orientation of S. That's our definition of positive orientation. If you could imagine, I need something, well, this milk jug, for example. Ignore the milk, everything else, but this is a closed surface because there's no point. I can't take a point on the surface and not have every different direction that's filled. But once I take the cap off, though, then this has a boundary. It's that right there. I don't know how to better explain that. Yep. Attendance.
I think Gauss put in more work.
Oh, I don't have it, actually, so I can't do it. Sorry. So joke's on all of you. I will count everyone as having reminded me for attendance today. Attendance points for everyone! This has nothing to do with course evaluations, just to be clear. My grading doesn't get easier.
This is the Bernie Sanders plan.
The fact that I emphasized that I drop your lowest test grades and replace it with a final exam grade were helpful, and it is usually helpful to most students. Me emphasizing that now, nothing to do with course evaluations. Just to be clear, nothing to do with course evaluations. Let's see here.
But you forgot to mention the strings attached with homework grades, right?
Oh, yeah, yeah. I, of course, check for... Thank you. I almost forgot about that. Phew, okay, good. But you guys have done your homework, so I think that's a moot. I mean, that's... What's that? I said that if you've done your homework, then I'll do that in the syllabus. I'll replace test grade with final exam grade if you've done your homework. But you guys have done your homework, so yeah, okay. You know, honestly, if you haven't done your homework, just don't take the final. I mean, there's no point in it. What's that? The daily, I need to update them soon. I can tell you what you have if you give me, if you ask me after class, I can look it up.
So is like the participation rate and the daily quiz like all one, or how does that work?
I don't remember right offhand, but I think.
100 for daily quizzes and then 20 for participation.
Oh, yeah. The 20 for participation. I just reserve that 20 in case there's a person that I just personally don't like. So I have something to like take away from them just because they're a bad person, you know. And so just on the off chance I don't like somebody, I leave that 20 there. So I have something that I can like, you know, get them with. But I'm just kidding. I almost always, I give everyone the 20 points. I don't know what that's there for. That's there for something. I leave that 20 points there for some reason.
Probably mandated by some course evaluation in the past.
No, it's something.
If somebody needs, like, if they're like at 20 points, it's done at a higher grade.
Well, yeah, I could take it away from them. No, I really, you know, I'd be happy to give everyone an A if you earned it. It would not bother me, honestly. I don't, you know. But anyway. I don't know. I don't think anyone will lose those 20 points if you've generally been to class. So how could you lose the 20 points would be if you had, say, missed 2/3 of the class. I might give you 10 points instead of 20 or something like that. Yeah. I think everyone who's here that doesn't apply to. So. I mean, it beats the posted attendance policy, right? Anyway, any questions about the test tomorrow? So, should you use this Stokes theorem and divergence theorem for everything? Not necessarily, right? There's likely to be a question on the test where I do actually expect you to calculate from the definition. How can you tell something is definitely involving a theorem? How about this? This is the smoking gun. You know, I have problem. Apparently I can't write today. And I say calculate the integral of f dot dr over c, where c goes from 0, 1, 2 to 7, 8, 10. If I ask this question, and I do not tell you specifically what C is, if I just say it's a point going from point A to point B, right? I don't actually give you a parameterization of the curve. There is only one possible way this question makes sense. F is conservative, right? So this is not an invitation for you to parameterize the line segment between those 2 points and to actually do that integral. What you should do in this kind of question, if I ask it, is to find the potential function for f and use the fundamental theorem of calculus for line integrals, right? So, you know, for example, if f was, I don't know, say like y, x, z squared, you're like, aha! So this vector field f is the gradient of what? Xy plus what? 1/3 z cubed, right? So when I integrate, I can't write today, guys. I'm sorry. F dot dr over that curve, I can just take f of 7, 8, 10 minus f of 0, 1, 2, right? And then you plug in whatever that is, 56 plus, 1,000 over 3 minus something that doesn't matter. Let's see here, 8/3. Yeah, there you go. On the other hand, right, there are other problems which you just need to calculate from the definition. For example, my computer turn off? Really? Okay, good. I never know when it's actually not really plugged in these days. How about something like this? What if you're asked to integrate? Seriously? This could get annoying. Let's see here. Integral of x dy plus x squared dx, something like that, over C, where C is, let's say, x equals to t and y equals to te to the t. I don't know. Whatever. 0 less than or equal to t less than or equal to 1. Well, is that a conservative vector field? So you're looking at the vector field x squared x, right? Is that conservative? What's the two-dimensional vector field? You want to check something, a 2D vector is conservative. You need what? The quick check is we need that qx is equal to py. If that ain't the case, it's not conservative wherever those conditions fail. If those conditions are met, if they're met on a simply connected region, then we have that there exists a potential on such a region. But beware the vortex example, Anyway, that condition's not met, right? 0 is not equal to 1. Am I right? We can agree 0 is not 1, right? So it's not conservative. I cannot do a run around of the problem. I just have to face the music and calculate this one, right? There's no other kind of sneaky way to do it. On the other hand, if you've got something that, if you see something like this, you're supposed to calculate. Here's the curve C. C is the boundary of a rectangle like that, and you're supposed to calculate the integral of x squared dx plus y squared dy over the boundary of the rectangle over that curve C, something like that. I don't know, maybe it's y.
The boundary doesn't make sense though. Half the equations are wrong.
Oh. But that could be still a sensible problem. See, because then you could calculate the integral all the way around, right? So they're half right. Wrong? Right. Oh yeah, these are kind of messed up. So let's see here. What if I did, so here they're mostly right, with the exception of, where are they mostly? Oh, it's still wrong. Thank you. Okay, now we're good. All right, anyway, sorry, I was not trying to do that. Anyway, my point is, if you've got integral around like a square or like a semicircle, maybe that's a Green's theorem problem, right? I mean, because then you can convert the integral around the edge to the area integral using Green's theorem. Do you understand the difference between flux and work for a two-dimensional case, right? They're different. How do you calculate the work done by PQ? Yeah, integral along C of PQ dot dr, right? The flux of the vector PQ through C, what's that? How did it go? I forget exactly, but it was P comma Q dot the outward normal the arc-length integral of that, right? And that worked out to something in the differential notation. What was it? I always forget this, but you guys have a card, so you don't have to forget it, right? Help me out. Let me write it down. What's that? P dy minus q dx, all right. I always remember that the p's and the q's are flippy-flopped from their respective components, and there's a minus on one of them, but I can never remember which one it is off the top of my head. I should come up with some sort of stupid mnemonic to remember it, but I just haven't. Any questions? Did I post an old test or something for you guys? I did. Any questions about that? Your actual test is likely to be shorter because I've gotten lazier. Like, I don't take joy in grading. I don't know about you, but you probably don't grade, right?
We're going to use like a specific theorem. Is it most likely going to be stated, or are we just going to have to know what to use?
I want you to be aware of when to use it. I don't want you to have to be told. But I might tell you to use it also. So I'm being vague, yes. That's definitely part of the test, is deciding whether or not to use a theorem. And where is it appropriate to do that? Also, how do you decide if a vector field's conservative or not, right? We learned that we can take the curl of the vector field, right? If the curl's non-zero, then that's a dead giveaway, not conservative. But there are other things that are trickier, right? It could have, we looked at this example, right? The curl was 0 everywhere except for that one pesky point in the middle, right? And so the fact that we have an integral around the loop of that particular vector field, right, which was 2 pi, that says that that vector field f is not conservative on the punctured plane. I've probably spent an hour in here talking about this. Wouldn't be surprising if I tested on that, right? That's a little bit subtle, because the question is, I mean, yeah, the curl of f in the two-dimensional sense is 0 everywhere except for where the vector field's not defined at the origin. And that place where it's not defined ends up somehow contributing 2 pi in the integral. If the vector field's conservative, we have 4 different characterizations, right? There exists a potential, path independence, integral around loops. Any loop is 0. This is a loop. This is 2 pi. So the vector field's not conservative on the punctured plane. So that theorem I stated about equivalent conditions for conservative is important to me. I try to test on that. But am I going to test on the proof of Green's theorem, or really the proof of any of the major theorems in here? Probably not. The only thing I might conceivably could test on reasonably would be the proof of the fundamental theorem of calculus for line. The one I used over there, that's actually just the chain rule and fundamental theorem of calculus. That one's pretty easy to prove. That's about the only one that's reasonable to ask you the proof of. Anyway, I shut up. See you tomorrow. Oh, you're probably wondering what we're doing the rest of the week. The answer is what? Quizzes. Well, hopefully, if things go well, I'll have your test graded to give back to you Wednesday. We'll have that class day, and then that's probably going to be our last class day. So, I mean, if that's okay with you guys. Yeah.
Will you have office hours between then and
I have my regular office hours, yeah.
If we need daily quizzes, can we just do them all?
Oh, I'll fix the daily quiz problem. Don't worry about that. But I think that's a little bit too much. So we should plan to still have class maybe the Tuesday of exam week, just to do a general review of the course. Any questions you have, we'll come together and plan to meet the last Tuesday of class. That'll be our last meeting. So meet tomorrow. Excuse me. You have your test tomorrow. Hopefully I give you back your test Wednesday. If I'm not done grading, we'll push we'll cancel Wednesday and meet whenever I have it done. I will let you know as soon as possible if that happens. I'm going to finish grading it Tuesday, don't worry. So we'll meet Wednesday. We'll take off Thursday, Friday, and Monday, and then Tuesday, review for the final, okay? Yeah.